We're good? Time to start. Great. Thanks everyone for coming. This is Diagnostic Tips and Tricks for JavaScript Windows Store applications using Visual Studio. Quite the mouthful. Basically, what we'll be talking about today is diagnostic tools and some of the cool tips and tricks that we can use with those tools to diagnose issues in JavaScript applications targeted at the Windows Store. This is Dev B313, make sure you're on the right room. My name is Jonathan Turner. I'm a program manager with the JavaScript languages and tools team at Microsoft. So we're going to break this down into two separate parts. The first part, we'll be talking about the debugging tools that we have available for the JavaScript applications. We've got some specific breakdown under there, scripting and native. For those of you who have tried to debug both at the same time, I'll show you some cool tricks there. Contract debugging, background tasks, and debugging applications that are already installed that you may or may not have a Visual Studio project for. We'll also be talking about performance. How do we deal with performance issues with Windows Store applications? Here we'll specifically be looking at tools that look at UI responsiveness. We'll look at how to do profiling and memory analyzer. Really what we want to do in this session is to give you a solid understanding of the tools that are available for diagnostics in Visual Studio 2012. I know we just announced the 2013 that everyone's excited about this. This session is for the tools that are already available in the Visual Studio 2012. So let's get kicked off. Debugging tools. In the debugging tools, you'll see that when you open up your debugging, you generally only have options for either the native or the script. But for some applications, you may want to be able to debug across both. You may have some parts that are in the native side and some parts that are in the JavaScript side. So I'm going to show you a demo of how you can use the tools as they stand now in Visual Studio to debug both. So I've got an application here. And what this application does is just basically connects to Bing, gives us a map view, and we can search. For example, let's go from New Orleans to, where are we next time? Houston? All right. Let's get directions. So as we get directions, you'll see it goes, it optimizes the trip, it comes back, and gives us our path. What we'd like to be able to do is to see how that happened. So we want to be able to debug both the JavaScript side that's showing us how this route is being printed out, but also the C++ side that helps do some of those calculations. So I'll stop this, and I'll set my breakpoints. So I may, kind of naively come in here and set a breakpoint in. Format time sounds like a good place if I want to get a sense for how those times are being figured out. And I may kind of look through the code and see on the C++ side that there's also, maybe a little bit down here, we see a compute length of route. Okay, so it seems like this will get us close to the right direction, getting a feel for the code. So we'll set some breakpoints, and then maybe from those breakpoints we can walk around and see the code kind of from those both angles, from the script side and from the native side. We'll give that a try. So we'll do the same thing, New Orleans, to, let's say, Houston, Texas. Say get directions. So it still goes through the same optimizing the trip. And we'll give that a second. And we jump directly to the JavaScript. And if I take this breakpoint out, because I want to see if I also hit that C++ breakpoint, I hit continue from here, and we jump straight to already having the route. So for whatever reason, that C++ was never hit. So let me show you an interesting trick to see both sides, both the C++ and the script side when you're debugging. So we'll start this again, and we'll start with the same breakpoint on the JavaScript side. But let's ignore the one that we've set up on the C++ side for now. I'll run the app, I'll get it ready. And then what I'll do is I'll come over to a second instance of Visual Studio. From this instance, I'll open that same C++ file that we had before, and we can set the breakpoint in the same location that we were setting it earlier. This time, though, what I'll do is I'll attach to the running instance of that application, this Bing Maps application. We'll see that down here. I can attach and make sure that when I attach, I'm attaching to the side that I want. Here, because I'm looking at C++, I attach to the native side. Make sure that that's checked and only that's checked. Hit OK. And then I attach. So nothing has happened yet because we haven't triggered that code. But let's go back and run through the same steps and see how that works. I'll do get directions. And now you can see that we have hit the native C++. And we do get the ability to step through and do the kind of debugging that we would want on the C++. We can hover over the length and still see, we can see that it's 0. If I go ahead and remove that and continue, as we continue, we magically kind of jump over to the Visual Studio instance that hits the next breakpoint. So you can see this actually does kind of work to allow us to go back and forth between the C++ and the JavaScript and get our debugging. So while in Visual Studio 2012, there's no mixed mode debugging support, what we can use is multiple instances of Visual Studio. And those multiple instances, on one side, we can connect to the script side. And on the other side, we can connect to the native debugging. This allows us to give the focus correctly between the Visual Studio instances based on which breakpoint is currently being set. So for our next demo, let's talk about contract debugging. So Windows 8 has a number of contracts that you can connect up to for your Windows 8 applications, allowing you to get into the charms side of things, for example, into the search functionality, into the share functionality. And we know ahead of time that some of the code that we'll be running is not necessarily code that we'll be seeing in the debugger. So what we need is a way of attaching before we hit our first breakpoint, basically. So let me show you a demo of what that looks like. Let's close this application, and let's go open our next project. So for here, we've got a couple of contract examples. Let's take our search contract example and run that real quick. Make sure it's not already running. Let me close this also. Let me give it one more try, then I'll try the other demo. Okay. 2 tries is enough. Let me pull open our backup. So in this one, what we can do is we have connection to the share side. And that functionality is something that we don't have necessarily access to from the start. When we hit share, we would like to be able to catch it before that share occurs. So what we can do, if I close this, is that we can start a particular, like for example, in this we can right-click, click Properties, and under Debugging, we see that by default when this application is run, when we do a debugging session, It's started by default. But we may not want that. For example, if we have kind of a client and server, we may want to stop one while we prepare the other one. And without having to set up and find the perfect place for a breakpoint, here we can just say, when you launch, don't keep going. Let me tell you when to start. So that's a good way there that you can, as you hit the debug, keep that application from continuing. So here, as I was saying, this allows you to configure the project to start without actually starting and hitting breakpoints. You can start it in kind of a stop state that you can control. And then from your contract, which I didn't have a chance to show you, you can then manually start it. So let's talk about background tasks. So in this demo, what we'll be talking about is you've got some JavaScript application that happens at a particular interval, let's say when you cross a time zone. Now, you may not want to take your laptop and walk it across a time zone to get that to fire, right? So we need a way of actually causing that action to fire so that you can do some diagnostics based on that. What you can do here then, and I'll show you, is that we can register ways of firing that event from inside of your diagnostic session. So let me open that project. So this is under background task. So I've already set my breakpoint in the background task that I want to run whenever this occurs. But of course, when I start it up, I've registered the background task. But again, this background task is for when we cross that time zone, and we're not going to carry that laptop. So what we can do instead is register that task to occur on a particular event, and then that registration will allow the task to show up here in this dropdown. And now if we call this, it's kind of like evoking that we've crossed that time zone. And sure enough, when we call that event, we hit that breakpoint that we've set, and we can go ahead and step and do our debugging from there, which is a nice way of setting up debugging for those background tasks. So as I said, we can trigger those background tasks from that debug location toolbar. We can even trigger tasks on apps that aren't necessarily running. We just set them to bugging without launching, like we showed earlier. And so for our next one, sometimes when we're debugging an application that we've installed. Let's say we've downloaded a particular application, a Windows Store application, and we want to pull it up and be able to start debugging without necessarily having a full project and source to go along with it. Maybe we have the source, but we don't have a project to go along with it. So let me show you what that looks like. So in this demo, we'll be running the Cut the Rope. How many of you play Cut the Rope? I think the first time I started playing that, I stopped about 2 hours later. Yeah, this is a pretty addictive game for those who haven't tried it yet. So what we want to do is we want to open up this application, and we want to be able to debug Cut the Rope. So let's try to do that. So actually, let's keep it running. And then what we'll do is we'll attach to Cut the Rope from Visual Studio. Let me start a new instance here and connect. What we can do from here, actually, is under debug installed app package, Cut the Rope. And we're only going to be debugging the script. So we've got a few options here. We can stop at the first statement in the application when it starts up. But let's go ahead and just let it run. Actually, I may have to close the other one first before I run it this way. So let's do that. One more time. Debug installed app package, cut the rope. Start. So because it's under the debugger now, it's going to come up a little bit slower. But what we can do is we can switch back over to Visual Studio. And we're starting to see some of the code that's been loaded while Cut the Rope has started up. So we've got some JavaScript files. We've got some Xbox util JavaScript. To show that we're actually looking at the actual application, we can set breakpoints in, for example, the leaderboard.js file and say, well, whenever we print, let's say whenever we print the high scores, we want to stop and see how that handles it. So we'll go over here, we'll click on leaderboard, and of course, as we begin to print the leaderboard out, we hit that breakpoint, and we can step through and do it this way. So notice we don't have a project, but what the Visual Studio has done is it's watched all those JavaScript files get started up, and as each file is loaded, the file that's loaded is kind of captured in this list, this script documents list, and then it allows us from there to go ahead and set breakpoints and take a look at the JavaScript code as if it was part of that project. All right. I feel like stopping and asking for questions already. That's a lot of data. So to recap, when we don't have projects, what we can use is use the debug installed app package feature. This allows us to look at any of the app packages that have been installed, all these Windows 8 or Windows Store style packages, and then we can connect to that application and debug it from inside of Visual Studio, setting our breakpoints and doing all the kinds of analysis on the debugging side of things that we would normally do. And as I showed before, you can click that checkbox and then stop the app before it's even started, in case you need to do some kind of configuration or whatnot. So that was kind of the debugging side of things, and now I'm going to show you some of the performance tools and techniques that we can use for these Windows Store JavaScript-style applications. So the first tool I'll show you is called the HTML UI responsiveness tool. The HTML UI responsiveness tool allows you to look at how your application is using the UI. It gives you a sense for if you have a slow startup time, for example, and you are trying to figure out why that slow startup time is happening. You can get a sense from this. Are you loading a lot of images, for example? You'll see all of the images you're loading show up in the tool, and I'll show you that in a second. This allows you to actually look at a whole bunch of other things too. So not just, for example, images, but CSS calculation, garbage collection, and so forth. And this is currently available. So let's take a look at that. So I'll switch us over to the project we'll be using for our performance demos. And we'll just take a quick look at this application so we can get a sense for it. Notice it is a little bit slow to start up, so we might want to take a look at why that might be. Generally, this is a kind of an image view application, but we're going to give it a few extra features. And as we give it extra features, we'll see how the performance shakes out. So that seems a little bit sluggish too. So let's go ahead and see if we can get a sense for why this is taking so long. So under debug, under JavaScript analysis, UI responsiveness, we can launch the startup project. So we'll just launch this again. We'll let the ETW kick in, and then we'll do the same steps we did. Since we are only really interested in kind of the first few seconds to see how that startup time happened, let's just pull open and look at the first few seconds of this. In fact, we can already see here that over a half second is image decoding. We can mouse over it, scripting and image decoding, rendering, and so forth. So what we can do with this information is we can now, with an eye to where we're spending a lot of our time in startup, we can go back to our original JavaScript and see if there are places that we can help speed up. So the first one is, if we look at our HTML, are there places in our HTML that are doing a lot of image decoding, or calling a lot of images? And as we look through, we may remember, oh, this was something from the other day that I added for debug purposes. It's doing a little extra crunching that we don't necessarily want to be doing. So we can comment this out and then rerun the tool and kind of A/B compare between our sessions to see how we've improved those startup times. So let's go ahead and try that and see if we've done any improvements. That seemed a little bit faster to me. I don't know about you. Let's stop and take a look. So you notice that in the first half second, where we were pretty packed in before, we're already starting to see some gains. Now, when you actually use a tool like this, you don't generally look out and find the one thing, just like we didn't necessarily find it here. But we're already starting to see incremental improvements. And this allows you to continually drill in and really knock down your startup times by continually looking at those diagnostics. So that was the UI responsiveness tool. Next, let's talk about the JavaScript profiler. So this is an instrumentation-based profiler. This means that it's going to go in and instrument the code. It's going to be a little bit slower because of this, but then it will give us nice, accurate runtimes. Before we do that, though, let's go ahead and talk a little bit about some of the terminology. When you're using these tools, they'll use, it's helpful to talk and get this in our heads so when we see it, we can understand. So there'll be inclusive time and exclusive time. Inclusive time was the beginning of the function being entered to the time when it's exited. And exclusive time is just the code spent in the function body itself. So let's see how this works. We have alpha that calls a beta. And let's say that alpha takes 30 milliseconds. Once we call beta, beta takes 50 milliseconds. And for practice, so I'll give you the first one. Beta takes 50 milliseconds, which we knew. So inclusive time would be 50 milliseconds. So what would be our exclusive time for alpha? So the exclusive time for the alpha, remember exclusive is just the time that's spent in the function itself. 30 milliseconds, that's right. And then inclusive time for alpha then would be 80, that's right. So here we get a sense for, if we're looking at a particular set of time, the time that's spent in total will be that inclusive time, and the time that's specifically just the function itself, not necessarily the functions it calls, will be that exclusive time. So let me get set up here for the next part. All right, so I've just run the performance, the profiling for this function. And we're seeing that we've already started to see some hot paths. This onReady state change looks like it's some hot paths. the UI has some hot paths, and we can take a look at that. But what I want to do is I want to kind of use this as a baseline, and then I'm going to add some functionality to this pond application, and then see if, as I add new functionality, to make sure that we're still performing well, we'll kind of come back to this. So let's take our pond application, and we're going to give it some new functionality. I've just worked with another developer. She had this great idea. Let's go back to the pond, and let's actually make it feel like a pond. So she gives me some code here. Let me find where my code is. So down here, she's like, oh, there's this great ripple function. I want you to try this out. So let's take a look to see what this looks like, and then see how we can improve upon it. So as I click, which you maybe will see, I may actually need to run this under, let's try this one more time. I'm going to run it not under the debugger, and so you can see what this would feel like as a full application. So there we can see kind of a ripple effect, if you guys can make that out. It doesn't quite have the same kind of speed and responsiveness, so we can use that tool to tell us why that is. So let's do that. I need to come back and quit this because we didn't run it under the debugger. And now we'll run this using our tool. So we'll start the performance analysis. We'll let this start up, and then we'll do those ripples. Notice, of course, that this is much slower, but this is because we've instrumented the code with all the analysis information that we need. So let's stop the profiling. And what we could have done earlier, too, is pause it, go directly to the time when we're running those ripples, unpause it, catch the ripples itself. So that's a good technique, so you don't have quite as much data. So we'll have to crunch through a couple of extra seconds here of data. What this is going to do is it's going to pull up that same report, but now we can get a sense for where that hot path may be in that ripple that we want to improve. So we'll let this crunch. You have to forgive my slow laptop. Actually, let's do what I said earlier, because I'm not sure how much data I collected. And because we're doing this particular instrumentation style, we may get to the point, just like I got to, where there's so much data that it's going to just take too long to run through it. So let's do it one more time. This time, we'll make sure that when we start the performance analysis, now we pick Start Performance Analysis Paused. This will allow us to get to the particular point in the application that we want to capture, knowing full well that when we're capturing it, we want to be really cognizant of how much data we're capturing. So we'll start on the page that I want to capture the data for. And now I can say Resume Profiling. We'll resume the profiling. We'll click once or twice, and that may be enough. And then when we come back, we can say Stop. So instead of capturing 5 or 10 seconds, which may be too much for some computers, what instead we can do is capture half a second to a second, hopefully capturing that specific spot that you want. And again, we'll let this data crunch. So when it comes back, that was much snappier. So that does definitely give us a feel for how much data it's having to work through. Here we see a slightly different story. Whereas before we saw something about images, now we're seeing this ripple function we've just added is really becoming the predominant use of the CPU. And the hot path really is this guy right here, math.floor. So this is a systems, JavaScript systems call. And if we go back and look at the code that we created, we've got this ripple. Let's see if we can find where that is. There's the pond, pool, ripple. Here's ripple. So in ripple, we knew ahead of time, because we did that analysis, that math.floor is going to be part of this hot path. And sure enough, it shows up 1, 2, 3, 4, who knows how many times. So you might think, OK, math.floor, is there a faster way that we can do math.floor without doing math.floor? And then you go and read up on math.floor and find that it actually does extra checks that we don't need. We know ahead of time that this will be a number, and we know that we just want to do a very basic floor. So we'll go and grab this code. And in this example, what we've done is we've done the same math.floor without doing math.floor. We use a trick using shifting to take the number and to floor it for us. So when we start this up, and let's go ahead and start without debugging so we can see what this would feel like on our user's box. We're back to the pond. Now when we click, these are noticeably faster. So we can see that analytics that we did was enough information to tell us where that hot path was, and then to kind of drill in and fix just that issue. So there are other tools that you can use to give you a sense for how ready you are for the Windows 8 store or the Windows Store. They cover a whole gamut of different things. Activation time, UI responsiveness, and so forth. You can see the list. And there are tools that you can run against to show you how close you are to being prepared. There's the whack tool, which is a tool that you can run on your JavaScript, and I'll show you here in a minute. There's the performance analyzer that you can also download and run. And these give you kind of a printout, which I'll show you, of the different pieces of your application and how you do in each one of those. So because the system is running a little bit slow, I'm not sure I'll let the whack tool run all the way to completion, but I just wanted to show it to you. So this Windows App Certification Kit, you can pick Windows Store, desktop app, device, and so forth. And because we're doing Windows Store apps in this session, I'll click there. And then it's going to go and find information about my system. And then it will list all of the available apps that I can get certified. So the information, so it's pulled in that information, and it will use that information. So now I can, you see I've got kind of a variety of different apps on here. The one I want is this pond app. So if I say my pond and I click next, it will begin doing a series of tests on it. You'll see it start up the app, close down the app, and may do this. I'm not sure how long this will take. It may take like a good 10 minutes. But it's doing like a thorough check of all the different components in your application, how it's doing under those different criteria. So you can see it here. It's starting up. It's taking a look at how long those image load times are. But let's go ahead and cancel that. So that's gonna wind down. So the kind of information, I may actually have a diagnostics whack results. Sure, how do we see if I can load these here? So I'm not sure exactly how to load these, but you can actually, as this finishes, because these are pretty long running, you can get the XML output. So I will just kind of open that, and we can, squint at it. But it's a very thorough breakdown of how different pieces of your application did, how long each piece did. And then in the WAC tool itself, it would show you kind of a visual breakdown of those components. So for example, one of the things that these tools may find out is that you're using a lot of memory. Say you're leaking a lot of memory. And you might think, well, in JavaScript, doesn't it have a garbage collector? Like, how do you leak memory? But if you've held on to, for example, large images, and then you've held on to those objects, you can imagine everything continues to hold on to objects. That's how you might leak some memory. So this would be unintentionally retained memory. What we can do to find out about this is to use this snapshot-based tool. And what it's going to do is we can run our application, and then we can take a snapshot of the application and its usage of memory at a particular time, do some work, and then take another snapshot. And then we can compare those snapshots against each other. This shows not only the JavaScript side, but if we're doing DOM elements or we're retaining images and so forth. Before we get into this, though, let's do a little bit of terminology because there may be some confusion. So the size of an object is how large the object is in memory. But the retained size is not only that object, but the amount of memory that it is basically preventing the garbage collector from retaining or reclaiming. This is probably best explained with a picture. So we've got object A, and it has references to object B and object D. Then we have object C, which has a reference to object D. When we're calculating the size and retained size, the sizes of all the objects are already known. We've got 100K and so forth, which we can see from the graph. But the retained size is, again, how much memory that object not only itself is holding, but it holds references to these other objects and prevents them from being reclaimed. As you can see in this graph, only one thing points at object B. And so the retained size of object A isn't just that 100K. It's also that 500K that object A is holding on to. Notice nothing else is holding on to object B. So if we removed object A from memory, object B would get collected. But because object A is sticking around, we have to hold on to all of object B as well. Can anyone guess what object B's retained size is? 500, that's right. So object B doesn't hold on to anything else, even though it's being held on to by object A, because it doesn't have a reference out to anything. Its retained size is only its own size. Object C's retained size, anyone know what that would be? 50. Because object A is also pointing to object D, the retained size of object C is only its own size because another object is pointing at object D. So object C is not solely responsible for object D. Object D's retained size then is 100. That's right. So this gives you a sense, a feel in a picture for when we might be retaining memory in a garbage collection scenario that we may not intend to do. All right, so let me get the memory profile ready. Does anyone know what that is? Feels like someone's watching TV in the back. Okay, so here we've got, maybe I did it really quickly, so let me just show you again. Under debug, JavaScript analysis, memory, there is this memory tool that we can run. And you can see it already starting. So what we can do is, as we start it up, we can take a heap snapshot. What this does is it gives you a little pretty picture of what the app is doing at that point in time. It gives you a sense for how much memory is in the heap. I could, for example, drill into it, and it would give me a lot of information. Let's say I don't necessarily want all that much information. I just want to get an overview. So we'll see that as how much is in the heap. When I do some work, let's say I come over to this pond and I cause some ripples to happen, I can take another snapshot. And then when I go back, I can kind of keep taking snapshots. You can see already when I went back, I'm now holding on to more memory than I initially had. Well, that's kind of strange. When I started in one place and I go into some page and I come back, I shouldn't be retaining yet more memory. So what we can do is, using that knowledge, we can see what might have happened in going into that page, and as we leave, checking to see if there are things that we could remove. Make sure we're not retaining any of that memory. So let me pull up in pool or pond. So pond is where that was happening. And under pond, as we're transitioning out, well, let's just take a quick look at what's going on. We've got water, which is creating a new pool in this register ripple effect. And then we're rippling happily along. And then when we leave, we unload, but we don't unload whatever pond was holding on to. We may have, or I should say water was holding on to. So we may want to just cancel the water. So let's try that. So I'll move water up here so that I can cancel it. And then we want to make sure that we're using the same one. And here we may say water dot cancel, I believe. So let's try that. So let's actually run this again under the memory profiler and to get a sense to see if we've actually corrected the issue. We'll do the same thing. Here we take a heap snapshot. We'll take a snapshot after we go in and create a few ripples. And we'll come back. That was weird. That was like all the way out. Let's try it one more time. So we'll try this one more time. We'll go in, we'll take a snapshot here, create a few ripples, take a snapshot. And then when we come back, so something was wrong. Let's take a look at that code again and notice perhaps when we're debugging, when we're canceling, what we actually might have meant would be, let's just set the water to null or so forth. So here, what we can do is, take the code, take those snapshots, continue to tweak the code until we work ourselves to where we're canceling and removing the objects that are unnecessarily retaining those images. I believe there's a cancel or null here that we could use. So with that, we covered a lot of ground. There's a lot of diagnostics for the Windows Store applications that cover the gamut from applications that you've installed on your system, ones that have C++ and JavaScript. So for example, you may want to debug both sides of that. And I showed you how you could take multiple Visual Studio instances, run multiple instances, and connect to different aspects of the application. We went through and looked at the different other tools. So if, for example, you're using charms and wanted to debug those charms, how you could pause the application before you started to debug. We looked at other ways of debugging, and on the analysis side, tools like the UI responsiveness tool and the memory tool. So let's open up for any questions to see if anyone has any questions. Yeah, we've got some mics that you can walk up to. Yeah, there's mics in the aisles. Definitely come on up.
Hello. Oh,
yeah.
Hello?
Yeah,
okay.
it's on.
Yeah, when you were debugging the installed package for the Windows 8, you happen to go to the source code, right?
That's right.
Does it mean that for every installed Windows 8 package is not secure, somebody can just pick it up, debug, and see the source code?
So for the Windows Store applications written in JavaScript, that JavaScript is available to be read by the user. Now you could, for example, there's a technique called minification and obfuscation, so that the code doesn't really look readable anymore. You know, all your variables turn into one characters, and you can make it seem very much less like the JavaScript code that you wrote, so that it's more difficult. But really, when it comes down to it, JavaScript is JavaScript. It's just a scripting language that you're running. It happened in this particular example. I didn't show you the minified side. We took a breakpoint into the JavaScript application where you could read it pretty easily. But some of the other engine stuff is written in that minified style.
The JavaScript profiling details that you were showing, what if we have to perform the same act on Windows RT? So we want to profile it, but we are interested in looking at JavaScript's performance when it is running on a chakra which has been written for WinRT.
Right.
So there's no Visual Studio that, typically you install Visual Studio on an x86 machine. So could this be done remotely in that case, or how does it work?
I'm not sure which tools work remotely. I think some tools of that set of tools that I showed you, I think some do work remotely where you could connect to like a remote RT device. But I couldn't tell you offhand which ones are capable of doing that.
And the second one is for the debugging section, you showed the capability of debugging an app, as the gentleman was asking, where you don't have code, Windows Store app. Can you profile it as well?
So for an app where you do not have the code,
right?
I'm not sure. You would have to have some code that you were trying to run against that it's giving you those symbols for.
Just like we are debugging an installed application package, can we profile an installed application package?
Right. Yeah, I'm not sure.
Okay.
Any other questions?
Hi. Are these techniques applicable to for web applications as well, or just for Windows?
So these were predominantly for those Windows Store applications. Some of the tools may work for when you're starting up. You can start up also in like IE. Some of the tools may work for those IE kind of startup sessions, like the debugging especially does.
Right, but not the profiling, or.
I'm not sure about that. Okay. They may, but I'm not sure. Any other questions? All right. Thank you so much.